Okay. Thank you for the banner IDs. Okay, so my name is Laura. I'm here in the Science Center in Frio 111. We're going to be going over today naming and uh, naming compounds, writing the compound formula, as well as oxidation numbers. So hopefully it won't take too long, but this is important for everything. This is a main topic that everyone's been coming in for questions. So, all right. Let me fix this video here. Okay. Yeah. Okay. So here I've created like a little flow chart of how naming works. For the most part, it's just going to fall into three different categories, which is going to be either it's molecular, it's ionic, or it's an acid. So this is just to help you organize like that looks like when you're actually figuring out what am I looking at. So for molecular, that could also be called covalent, is going to be two nonmetals when there's two nonmetals together, and we'll go over like where those are on the table. And molecular compounds are where you use these prefixes. So these are Greek prefixes that you use to name them. So it's just the amount of how many atoms there are. So when you do name them, it's the prefix in the element. And I call it like a first name, but for the first one, it's the prefix in the element, and then the last name is a prefix, and then the second part is going to become IDE. So everything always changes to IDE the majority of the time. So if you have fluorine, it changes to fluoride. If you have chlorine, it changes to chloride. So all of those will be like sulfide, oxide, bromide, iodide, nitride, phosphide. So it's kind of like the pattern that you'll end up seeing. So the example I have here is CO2. So the prefix and the element. So if there's just one of them, you don't need the prefix. So that's why it's just carbon. And then for the second one, there's two oxygens. So the prefix for two is di. So then it's di, and then oxygen will become oxide. So it will be carbon dioxide for this compound. And the nice thing about molecular is that it's just prefixes. You only use prefixes for molecular. You never use it for anything else. The second one you're going to see is ionic. So ionic is going to be a metal and a nonmetal. And for ions, ions are all about charges. So those are cations and anions. Your positively charged ion and your negatively charged anion. So there's two different buckets for those. One is either it has a transitional metal or it does not. If you recall, we'll go over the periodic table again, but transitional metals are the ones in the middle. If it has a transitional metal, you have to use Roman numerals, and that Roman numeral always represents the charge of the metal. So like in this example, in this one, and we'll go over charges later as well. But for this example, the manganese charge is a 2. So that's why there's a 2 here in the Roman numeral. And this rule continues about turning things into IDE, so the oxygen will become oxide. On the other side, if you don't have a transitional metal, it's pretty much the same. It's just the cation, the anion will become IDE. So if you have something like NaCl, Na is sodium, and then chlorine will become chloride. And the last one you'll see in ionic is if you have a polyatomic ion. So if you see 3 or more elements, that means you have a polyatomic ion in there, and we'll go over those as well. But the same rules apply as cation and anion, except for this one, the polyatomic ion has its own special name, so you don't mess with it, you don't change anything about it. It's just whatever it's called, that's what you name it. So Na is still sodium, and this NO3 is called a nitrate. So when you name it, it's just sodium nitrate. And then the last one you might see is an acid, and these will typically have a hydrogen in the front. So that's how you will recognize that it's an acid. And then depending on how the compound name ends is like what it's going to change to. So for instance, this chlorine, if you were typically would be called a chloride. So you would follow the rule for chloride, which will be then become like hydrochloric acid. And so we'll go over the three rules for acids as well. This is just kind of a big picture overview of like how to name everything. So here we're going to go over the periodic table itself. So everything in the pink, like to this left, is all metals. So the majority of the table are metals. And then this blue little corner here, those are your nonmetals. And the green, we're not going to worry about too much. Those are the noble gases, but you're not typically going to be naming with noble gases. And then also, I'm just going to review the charges. So the charges are above each column. So this first column, all of this first column is like a +1 charge cation. And then this one is, the second column is a +2 cation. This column's +3, and then on the opposite side, you have like all these are -1. Oops. All these are -2, and all these are -3. Typically, like here, down here, like it kind of stops at this ladder, like at the metalloids. So these charges just kind of are for the blue area. And then here in the middle is a transitional, and we'll talk a little bit more about that as well. Okay. So here's kind of what I talked about earlier was if you're looking at a molecular or covalent compound, that's always the first question you want to ask yourself is, what am I looking at? So is this covalent, is this ionic, or is this an acid? So just to review again, for molecular or covalent, it's between a nonmetal and a nonmetal. So if we go back, that's very few of them because it's just this little blue corner here. So if it's covalent, it's present right here in this corner. And that's the only time you use the prefix. You don't use it any other time. And then here was the rule again, was the prefix and the element. And then the second one becomes IDE. So if you don't know what the Greek prefixes are, here they are. You will probably have to memorize these, so you can practice using those. But over time, you should be able to remember like what each of the prefixes are. But yeah, you'll have to remember these. So now we're going to do some examples, which some of these we already kind of did. Like this first one, we're looking at the name of the element, which is carbon. Oh, let me change the color on here. Carbon. And then the prefix for 2 is di. And then that oxygen is going to become oxide. So that would be dioxide. So that's the first one. The second one, we have a sulfur and a fluorine. The fluorine is going to turn to fluoride. And then we're just going to pop the prefixes in the front. So since there's 2 sulfurs, that's di. And then it's disulfur is 1. Oops, I misspelled it. But the second one, we look for 6. So 6 is hexa. And then that's going to become hexafluoride. So you'll have disulfur hexafluoride. And let's do the last one. Again, it's a 2 there's 2 carbons, so it's going to be dicarbon. And then the prefix for 5 is penta. So we're going to get pentanitride. Okay. So with naming and writing compound formulas, you always want to go backwards and forwards. So you want to go from the compound to the name, and then you want to be able to go from the name to back to the compound formula. So that's what we're going to do here. So phosphorus is a P, and then pentafluoride. So we're looking at an F for fluorine, and then penta was 5, so it's going to be PF5. And just so you're aware, like those should be like subscript numbers. It should look like P and then a small 5 here. I'm just not going to format that right now. Okay, so let's do the next one. Nitrogen is N, and then mono is 1, and oxide is for oxygen, so that one would just be NO. And then the last one is diboron. Di is 2, and boron is B. So we're going to do B2. And then tetra is for hydride. That's from hydrogen. So it's going to be H4. So as long as you remember these prefixes, these molecular ones should be pretty simple to go through. Right? Well, let me clear this drawings here. Okay. So now back to the ionics. Ionic is a metal and a nonmetal. So if we go back on the table, ionic is always a metal plus a nonmetal. And now we're going to focus on charges for ionic ones. So when you write them, the metal cation always goes first, and then the anion goes second. That second one is going to change to IDE. And then when you write the compound formula, the charges together should always equal to 0. And we're going to see like why that works out. So here's a little review of the charges again. Like we had said earlier, like this first column, group 1 is all +1 charge. The second one is all +2. This one is +3, and then it flips. So we get -1, -2, -3. Here we do get to see the transitional metals. So the reason they're called transitional is because they can have more than one charge. So if we look at this chromium, it could either be a 3+ charge or a 6+ charge, or this copper can be a +1 or a +2. So that's why they're called transitional. Not all of them transition. So the ones where it just has like one, they're in the transitional area, but I don't believe you have to put Roman numerals because they only have like that one charge. But that might be a question for your professor. So let's continue. All right, so when you're naming, again, the positive one goes first and then the negative one goes second. All charges must equal to 0. So here I have an example where the charge does not equal, like 7 plus is, like adding these together will not equal to 0. So whenever that happens, you do have to make some adjustments. And this way that I have here is kind of like a shortcut. So you're just going to crisscross the numbers across from each other. So the 3 will come down to the A and the 7 will come down to the B. So like this should be your final formula. And the math will work out to where it will equal to 0. And we'll do an example where like we could see why that works out. So let's do the naming of these first. So MgBr2, we don't use prefixes here. So all you do is like find the name of the element. So Mg is magnesium. And then bromine will become bromide. And that's it, magnesium bromide. So don't add anything extra. It's just the names of the elements plus IDE, no matter like how many there are. Okay, so Li is lithium. And then sulfur will become sulfide. And then this last one, Na is sodium. and then bromine will become bromide. Okay, so pretty simple. So here, when we go from the name to the formula, that's when more people have trouble. So here's where we have to focus on the charge. So sodium is in that first column. I'm gonna write on the screen here. Give me a second. Okay. So, sodium is a Na and chlorine is a Cl. And if we go back to the chart, or if you remember from the periodic table, Na is in the first column, so its charge is a +1, and chlorine has a -1 charge. So +1 -1, that equals to 0. So that formula is correct. Like if you were to write the formula for sodium chloride, it's NaC. So let's try a different one. So let's look at magnesium's in the second column. That's a +2 ion. Chlorine is still -1. So in this case, they're not equal and opposite, so we have to do a crisscross like we had in this example. So if we crisscross those down, our final formula will be Mg. It will be a 1, but we never write the 1, so you're just going to leave it as is, and then chlorine will get a 2 down there. So this will be the formula for magnesium chloride. And then let's do this last one. Magnesium oxide, magnesium's +2, oxygen is -2. So that equals 0. That's correct the way it is. So when you write your answer, it's just going to be MgO. You're not going to write any charges. This work right here is just to figure out if it's correct or not. When you write the compound, you're not going to write like charges or anything. So I do want to show you why the MgCl2 works out. Okay, so we said magnesium was a +2 and chlorine is a -1. So basically it's asking, well, how many more chlorines do I need for us to equal to 0? So if this is +2, I need to have like a complete charge of -2 on the right side. So that means I just need one more chlorine.
Oh, I'm just
So
this packet. Do I still have
then, your final formula will be MgCl2. And together that will equal to 0. So this was a +2 and a -1. Like if you multiply these two together, the 2 times the -1, that will give you the -2. And then this plus this equals to 0. So the shortcut works out, but this is why it works out. So that's to save you time, but you do need to understand like why it works. So that's why it works there.
Yeah.
All right. Moving along. So with the polyatomics, it was a compound that has 3 or more elements. So these are many of the common polyatomic ions. You can see that they have their own formula, their own charge, and their own name. So these you really don't mess with, like you don't change your name, you don't change the charge, you don't change like the formula. So let me see here. Let's look at some examples. Like this first one, SrPO4. Sr is strontium. So we're going to type strontium. And then PO4, you just look for it on the table. So PO4 is a phosphate. So that's just what the name is. You just look up what it is. And probably your professor has maybe 4 or 5 that you need to memorize. The rest should be provided for you or they're not going to ask about them. So I would check with your professor to see like what's you need to be memorizing.
All
All right, so this next one, Be, I believe Be is beryllium. And then OH, we look on the table, OH is hydroxide. So that's the formula, that's the name. And this last one, Na is sodium, and HCO3, that is bicarbonate. So Na, that will be sodium bicarbonate. Okay, so that was going from formula to name. Now we're going to do the opposite where we go from name to formula. So here, I'm going to write here. Let's see. So sodium is Na, and then nitrate, we just look from the table. So that's NO3. And then here we do need to worry about the charges now because we're writing the formula. So Na is a +1, and it tells us here that a nitrate is a -1. So since they're equal and opposite, we're good there. We don't have to make any changes. So the next one, aluminum is going to be Al. Aluminum has a +3 charge. And then carbonate is a CO3. And I'm blocking it on my screen, but let's see, it's a 2- charge. So that is a red flag because they are not equal and opposite. So in this case, we're going to have to crisscross. So our final formula will be Al2. And then we want to put this in parentheses and put this 3 on the bottom. The reason you need a parentheses is because if you had just written like this, that would mean 33 oxygens, which we're not trying to mean. We're trying to mean 3 of the carbonate ions. So we definitely needed a parentheses there. Okay. And then the last one, sodium phosphate. Sodium is Na, and that's a +1 charge. Phosphate is here. It is a PO4 with a 3- charge. So that's another red flag that they don't match. So we have to make some adjustments. So we're going to crisscross. Na will get a 3, and then PO4 will remain as just 1 PO4. Okay. All right. So that covers polyatomics. I'm going to move along. Let me clear my drawing. Okay. So with the transitional metals, the same rules apply as like naming ionic, except we're going to start adding in the Roman numeral. The Roman numeral is always the charge of the metal. So let's look at these 2 examples. We have iron, FeO. And if we want to name that, we know that Fe is iron, and oxygen will become oxide. But we need to figure out, well, what's the charge of the metal? So we do have this formula here. And iron is transitional, so it's either a +2 or a +3. And so how do we know which one it is? We're going to look at its partner. So oxygen is always a -2. And you want to ask yourself, well, what does iron need to be so that together I get a 0? And so the only answer is +2. Like iron has to be a +2. And then since we know the charge now, that's what's going to go into the Roman numeral. So then this would be iron 2 oxide for your name for your compound here. Okay, so that's how that works out. And let's do it the opposite way. Let's go from the name to the formula. So again, we know we're working with iron. We're oxide, we're working with oxygen. And then we need to get the formula. So this is telling us that the charge of the iron is 3. So it's telling me it's a +3 charge. And oxygen is always -2. So I'm looking at these and they're not equal and opposite, so we have to crisscross. So then your final formula should be Fe2 O3. So this will be your formula for iron 3 oxide. And I want you to notice that this 3, some people will think, oh, that's how many irons I have. That's incorrect. We only have 2 irons in the formula. It's always the charge of the metal. So make sure to keep that straight. And those are pretty much the rules for transitionals. It's just focusing on the metal, the charge of the metal. Okay, so now we're going to look at naming acids. So there's the 3 rules. There's 3 options you will see. It's if you have, I don't think I have an example for this one. This one we could use HCl. This is meaning like, what is the ending of the word we're looking at? So this is chlorine. Normally, when you name it, it would be chloride. So we're going to use the "ide" rule, which is hydro, and then whatever this is, ic acid. So that one should be hydrochloric acid. Wait, trying to type here. Okay, I messed up. It should say hydrochloric acid. So let's look at the second example. If something ends in 8, then it will become an ic acid. So that example is this one right here. NO3 is nitrate. So if it has a H in the front, it's going to change from nitrate to nitric acid. So that's just based on the name of this ion. So that ion is a nitrate ion, so you're going to follow that rule of becoming an ic acid. And then the third rule is if it's an ITE ion, so NO2, that's called nitrite. And if it's a nitrite and it's an acid, it's going to become us. It's going to have this us ending. So it's going to be nitrous acid. So those are like your 3 options when you're naming an acid. Each ending has 3 different rules. So I think you'll have to memorize those as well. So here's kind of like a pattern. So it's showing you that if it's a IDE, you're going to get that hydroic acid. So those are 2 examples right there. And then if you have ATE, that's just going to become ic acid. And then ITE will become the us acid. Okay. There are a couple of other scenarios, but for the most part, those will be the 3 rules you're going to follow. Another one you might see, which I didn't put on the flowchart that we had was hydrates. So it's kind of going to combine the rules for naming ionic compounds and then using prefixes. So if we were to write out like calcium chloride dihydrate, we can write out the formula. So calcium is Ca, chloride is Cl, and then we do have to check charges. So calcium's a +2, chlorine's a -1. Those are not equal and opposite, so we have to crisscross. So it will be CaCl2. And then the way you notate it is with like a little circle like that. Hydrate, we're going to be referring to water. So that's H2O. And then di, we learned earlier, is the prefix for 2. So this would be the compound formula for that hydrate name. Okay. And now we're going to go opposite from the formula. We want to write the name. So Na is sodium. And then CO3, I believe, is carbonate.
Y slash
And then 10 is deca,
this right
and then decahydrate.
cereal.
So that will be the rules, some examples for how to name hydrates and write the hydrate formula. Okay, so that was pretty much all the naming rules. At least with naming, it's very like logical. It always follows a pattern, it follows the rules. So as long as you know the rules, you can play the game. Okay, so learn the rules and you can get through naming like pretty simply. So the last part is going to be oxidation number. So I've put up a picture here of the rules for determining oxidation number. So we're going to apply these rules to some of the examples here. So let's go ahead and take a look at that. So we have a carbon and an oxygen. Typically, there's not a rule for carbon, but there is always a rule for oxygen. So I would go with the oxygen first. So like here, if we look at oxygen, it's -1 in peroxides, which is not that, and then -2 in all other compounds. I would say like 98% of the time, oxygen's oxidation number is -2. So it's going to be a -2 here. And then the second rule we're going to use is that the sum of all oxidation numbers in a neutral compound is 0. So there's no charge on this compound, so its charge is 0. So because this oxygen is a -2, this carbon automatically, its oxidation number is a +2 because together they need to equal to 0. So if they were to ask you for the oxidation numbers, you would have carbon as a +2 and then oxygen as a -2. So let's move on to the next one. Again, there's not a rule for carbon, but we can use the rule for oxygen. So oxygen again is -2. But now we have two oxygens. So in this case, you want to multiply that together to get like the total amount of charge. So the total is -4. So to equal to 0, the only option for carbon is to be a +4. So carbon would be +4 in this case. All right. If we have something that's just one element, that's going to follow this rule. Only one kind of atom present, its oxidation number is 0. So that's just what it is, 0. Even though I know it is oxygen, but whenever it's by itself, whenever any element is by itself, its oxidation number is 0. Okay, and then if you have a charge on the atom, like we have here, then that's its oxidation number. So this oxidation number is just a -1 because it told us the charge of the atom. All right, let's do this one. O4. Again, oxygen is still just -2. Chromium, there's no rule for chromium, so we're going to have to calculate what it should be. So let's find the total negative charge here is -8. So to equal to 0, chromium has to be a +8. And I do want you to realize like oxidation number is different than charges. Sometimes they are the same, but as you can see, like it can change. Like this oxygen was a -2 and now like over here it's a 0. So oxidation is more flexible. It changes depending on like what the compound is. And you'll see that over here as well. So um, let's do this last one. Oxygen, we can count on being -2. Potassium, let's see if there's a rule for. So we can use this rule right here, group 1A. Here's potassium. So that's a +1. So this is a +1. Okay, but there's no rule for manganese there, so we're going to have to figure out what that is. So let's figure out how many negative charges we have. So multiply that, that's -8. We had a +1 from the potassium. And then we still need to figure out the manganese there, but so we need to equal to 0. So it's like 1 plus what minus 8 will give us 0. So we need the positive charges to equal to 8. We already have 1, so I just need 7 more. So that manganese is a plus 7 oxidation number. So you're usually going to use some rule that's already present to find out the oxidation number for the other partner. So those are just some examples you can use. And I think that might be it. Let me check. Yeah, so my advice would be to get yourself acquainted with the polyatomic ions so that way when you see them, you know exactly what it is, where all the metals are in the table, the transitionals, the nonmetals. Practice like writing the compound formula as well as the name and going back and forth between them so you can get used to doing them both ways. And just that first step is always, is it ionic, is it covalent, or is it an acid? Because those three, it will change how you're going to apply the rules um, to naming and writing formulas. So that concludes the workshop. If you didn't already put your banner, I think everybody did put the banner ID. So I hope that was helpful. And if anyone has any questions, you can come off mute or put in the chat. I can take any questions, but that concludes the workshop.